Hello ladies and gentlemen, welcome back to the channel. Today we're talking about influence lines, and really the question with influence line diagrams is where will moving loads and live loads maximize the internal loading within structural systems? To demonstrate this this influence line objective, I'd like to start off by looking at an example. I have demonstrated a two-span beam here, and I'm telling you that I have a location, a point of interest referred to by x naught, and I'm interested in asking the question of what's the maximum shear and moment at location x naught introduced by a force at location x. So location x could be anywhere along this two-span beam, and the force being applied could look like this. It could have any kind of magnitude. It could be F. And really the question that I'm interested in is where will the force F be placed such that I have maximum shear or maximum moment at x naught? This is the question that we're going to be dealing with here. So to begin with, I'm going to introduce the principle of Muller Breslav, which is very interesting because it simplifies the process of obtaining influence line diagrams. So we're interested in the Muller Breslav process or principle. And so what the Muller Breslav principle states is that to determine the internal forces of a structural system, we need to assume some sort of alternative internal connections at the location of interest, like the x naught position, and to use the deflected shapes to guide the influence lines. So we're introducing some hypothetical internal connections, and we see how the structural system deflects due to these new internal connections, and then we simply obtain our influence lines. And here I'll show you how this process is done. It's really straightforward. To do this, let's start off by thinking about shear. So we're going to do one example for shear, then we're going to do another example for moment, and then another one for support reactions. So we're interested in shear, and let's say I have a beam that looks as follows. I need to make several copies of this line. I'm going to use it multiple times. Here it is. And lastly, here's the next one. I need 3. So I have a pin connection here. And I have a roller connection at the very far end. And the point of interest in this example is at the midspan here. So I have these lengths L, L, and L. And the question that I'm asking is, at what position can I put a point load that results in maximum shear at this position of interest, this position here? So with the Muller Breslav principle, it tells us that for shear, we need to introduce a slider. And a slider is an interesting type of connection because it results in vertical deflections in beams. And so if I have my original connections like that, and if I have this roller that I had early on, and I'm introducing this new slider, we call that a slider, what ends up happening is, with this principle is, on the left side of the slider, we're going to move the structure down. On the right side of the slider, we're going to move the structure up. So on the left side, I'll move the structure down, and on the right side, I'll move the structure up. Here it is. And At the locations of the pin, we're not going to have any motion. Pin does not allow motion. And at the location of the roller, we're not going to have any vertical motion. So here it is. We've introduced a slider that resulted in a vertical sliding in our beam. And what the Muller Breslav principle tells us is that the total amplitude between the maximum, this maximum position, and this minimum position must equal to 1. And so because these two lengths are equal, these magnitudes are going to be equal, 0.5. Okay? And because this is also L, this magnitude is going to equal to 0.5. And we're using simple geometry to obtain this kind of relationship. And so that's it's really simple. That's really it. Whenever you're using the Muller Breslav principle, you can obtain the influence lines for shear forces, and this is what you're going to get. The next thing is bending moment. So let's talk about bending moment. Suppose I have a beam that looks like that. It's a slightly different example. I like to introduce as many examples as I can, and given the nature of these lectures, they tend to be short. Examples tend to keep things compact and the learning much more simpler and effective. So with this new beam, I am given a pin connection at this position here. So pin connection. And I have a roller here. And the lengths given are L, L, and the point of interest is here in the middle. So we have L over 2 and L over 2. This time we're getting asked the question of find the location of the moving force that results in maximum bending moment at the location of interest. So bending moment is really what we're interested in now. So with the Muller Breslav principle, it tells us that we need to introduce a hinge at the location of interest for bending moments. So we introduce a hinge like that. And when we introduce a hinge, we move it up. And we're going to draw straight lines. Going to look like that. And another one is going to look like that. And I'll explain to you what we're doing. So based on this principle, anytime you're finding the influence line for the bending moment, you introduce a hinge, and the angle, the total rotational angle of this hinge, so between this arm and this arm, this rotation must have a magnitude of 1. If I have this magnitude equaling 1, and I know that I have L over 2 here and L over 2 here, then these angles are going to equal to 0.5 and 0.5. That's what those angles are. And so if I'm looking at this triangle, and let's see if I can draw a straight line. Oh, horrible. Let's try again. All right, a little better. And if I'm looking at this triangle, and I know this angle is 0.5, and I know this length here is L over 2, then I can really find out what this maximum value is at the location of the hinge. And this is going to equal to 0.5 times L over 2, and that'll result in L over 4. So that's really how we find the influence lines for bending moments. There is one more thing. We have to draw the influence lines for support reactions. So let's do that. So we're thinking about support reaction. With support reactions, it's going to be the same. I'll formulate an example. Another simply supported triple span structural system. I'll make a couple copies that I can use. Okay, here it is. And with support reactions, assuming I have two reactions here, a roller and pin, and these are A and B, and these lengths are L, L, and L. What the Muller Breslav tells us is that if reaction B, for instance, is of interest to you, what you need to do is to move it up by a magnitude of 1. So I move it up by an amplitude of 1. And then the other reaction stays in the same position. And this is what my beam's gonna deflect as, or deflect into. If this position here is 1, then on the far left I'll have -1, and on the far right I'll have a magnitude of 2. And that's really it. I used simple geometry and the relationships, the links that I have, and the vertical deflections that I have, and I obtain all the amplitudes. And so if I were interested in finding the position of a point load that results in maximum reaction at B, it will happen at the very far right, so where we have the 2.0. Now we're going to do examples, and we're going to use these influence lines, and I'll show you how influence lines are in fact used. Because so far what we have done is to simply identify what the influence line diagrams look like. There's going to be uses for these, and that's really where the important applications are. So we're doing examples now. And suppose I have a 2-span beam separated by a hinge. So I have a hinge here, and I have a fixed reaction on the left, and these are labeled A, B, and C. And the lengths given are 8 feet, 8 feet, and 20 feet. Then there's going to be a point of interest. We will call it point D. And we have a point load of magnitude 500 pounds that is moving across this double span beam. So the point is P is equal to 500 pounds. And we're interested in M max at D, and we're also interested in the position at which the M max is resulted in, or the position of the point load which results in M max happening at D. And so because we're interested in moment, we have to introduce a hinge at D. So our structure already has a hinge at location B, but we need to introduce a new hinge at the location D. So we're going to have our original supports. So I have the fixed support, I have the roller support, those are not going to change, and I have the location of the original hinge. And I'm introducing a new hinge. Of course, the fixed span of AD will not move because A is fixed and A cannot rotate. And because we're introducing a hinge at D, there's going to be a drop between D and B. B is where the original hinge was, and lastly, we're going to have the remainder of the beam going back up. And this is really how the structural system will look like when we're thinking about the bending moment or the influence line for bending moment. So we have a rotation. The Muller Breslav law told us to rotate by a unit of 1. So the left span of the beam, AD hasn't moved, so that rotation is 0. The right side has to move by 1. And if the right side is moving by 1, this length down here will be 8 times 1, so that's 8. And so if I'm interested in M max at D, I can say minus 8 times 500, and we have minus 4,000 pounds. Feet, because these are imperial units. And of course, the position at which M max happens is location B. Very straightforward. Influence lines are not supposed to be difficult, but they give us a tremendous amount of insight into how structural systems behave and how they should be designed, and where the locations, the critical locations of the beams are going to be. Let's do one final example. Examples are the best. That's how I learned when I was taking a course like this one. So this is our final example. And again, we have another double span beam. And again, it's fixed on the left side. There is a hinge here. And there's a roller at the far right. We have A, B, and C. And this time we have distributed loads. So we have a dead load, and its magnitude is 1.5 kilonewtons per meter. And we have a live load, and its magnitude is 10 kilonewtons. So my live load, as you can see from the units, is a point load, and my dead load is a distributed load. And the lengths of these sections are 5 meters and 10 meter. And so the question we're getting asked is A. What is the maximum moment at A? So max moment at A due to any arbitrary position or positioning of these distributed and point loads. And B, what is the max shear at B? So we're going to draw two influence line diagrams. One is going to be for bending moment, the second will be for shear force. So for bending moment, I am interested in MA and how it's going to vary with different positioning of loads. For MA, when I introduce a hinge at location A, there is going to be a drop since there's also a hinge at location B and there is a roller at C. It's fairly intuitive, right? We have this beam dropping here. That's what it looks like. And we have it going back up to its original position. And we have another hinge at this position. Okay, and because this rotation from the Muller Breslav principle is 1, we know that this magnitude will be -5. Now we're going to do the same thing for VB, and we know that there's a roller at C, and so this time, this is where our hinge is. This time the left span is not going to move, again, because it's fixed at this position. And when we introduce the slider, the right side of the hinge is going to go up by a magnitude of 1 per the principle, and it's going to go back down. Here it is. And so that's really it. We have this magnitude, it's going to be in kilonewtons, it's going to be 1. And so we go back down to C. C is the natural or prescribed boundary condition, so we're not going to change that. But we're only introducing slider at position B per the question, because we're interested in influence lines at, for the shear at location B. And so let's do the math now. Dead loads are typically applied at all positions on a beam. So with dead loads, we cannot select where it will be applied. It will be applied along the entirety of the span of this beam structure. So when I do the math, I'm doing MA, and I'm interested in the max value. I can simply say that 1.5 kilonewton per meter is applied at all positions. So I'm going to apply it and multiply it by this entire area, this entire rectangle. And the area is 15 times 5 divided by 2, because that's the area of rectangles. And then I also have 10. 10 will be the live load, it's a point load. I'll apply it at the position of -5, because that's the maximum value for point load. And so when I do this math, I should be getting 106.25 kilonewton meter. And next up, I'm interested in VB, and again, we're interested in the maximum value. Again, with distributed loads, you don't really have a choice. They will be applied along the entirety of the section. Now, because the left side is equal to 0, we're only going to pay attention to the right side. So we have 1.5 kilonewton per meter, 10 meter times 1 divided by 2 plus 10 times 1. And the resultant is 17.5 kilonewtons, being the maximum shear at location B. So really, influence lines are not supposed to be difficult. They're really straightforward, but they are very useful in design. And I hope this lecture has been useful. Go ahead and comment any questions or feedbacks that you have. It makes me more than happy to take a look and hopefully reflect on my teaching skills and improve in my own way. So I'll see you in the next lecture, and have a great time. Bye-bye.